Good morning, everyone. So, am I audible?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, no problem. I guess all of you has joined. I see 25 here. So I think all of you have joined, most probably. Okay. So I shall. I recall I have shared the syllabus with you. So did you get the syllabus in WhatsApp? Yes. So I
Yes,
have
sir.
shared syllabus with you. Okay. So actually, it's through online. So sometimes I feel awkward if there is no sound, and if there is too much sound, again there's problem. So sometimes one or two, please give response. Okay. Okay. Right. Okay. So, I guess you have gone through the syllabus. So I'll discuss the whole this paper with you. Okay. There are several topics already you are introduced with the topics. Okay. I guess you all are still safe and healthy. Please be careful and take care of yourself because health is important. This is one issue. Regarding the class, I have shared some scanned notes in LMS. So I request all of you to download these notes from the LMS. Okay. And during the class, I will try to discuss. And sometimes if there is calculations, I will tell you to do calculations in your notebooks. Okay. So you please do the calculations. This is one part. Sometimes I will give you homework. So you please do the homework. And after the class, within one day, for example, today I am taking your class and it is supposed to finish by 2 p.m. So by tomorrow 2 p.m., you all of you have to take the photograph of the classwork. Classwork means you don't need to copy everything what I am telling. Only the parts I tell you to calculate. Then the homework. You take the photographs of all these homeworks and calculations and make a single PDF file and send me by email. I will share you an email and also give you some guideline in WhatsApp group. You should do it regularly. Okay, because this will be helpful for me for assessment also, because in near future it's very hard to re-establish the physical mode class. I am not sure about it, but anyway, so you have to do it. Okay, so do you have any suggestions or query in this regard, Vidyut?
Yes, sir.
Do you understand what I told right now?
Yes, sir.
কি করতে হবে, আমি যখন ক্লাস করাবো ক্লাসের সময় আমার সব কথা তোমাকে লিখতে হবে না, কারণ এটা আমি নোট দিয়ে দিয়েছি। যেটা করতে হবে, যদি কোনো বড় ক্যালকুলেশন থাকে, যদি আমি বলি যে ক্যালকুলেশন করো, ক্যালকুলেট ইয়োরসেলফ, তাহলে তোমাকে ক্যালকুলেট করতে হবে কাগজে। এটা একটা পার্ট। আরেকটা হচ্ছে সামটাইমস আমি তোমাকে হোমওয়ার্ক দেব, যেটা আমি আগেও দেখেছো দিই আমি মাঝে মাঝে। তোমাকে এই যে ক্লাসের সময় যে ক্যালকুলেশন করেছো প্লাস যে হোমওয়ার্ক করেছো, সেটা আজকের ক্লাস যে টাইমে শেষ হবে তার থেকে, যে টাইম বলতে অ্যাকর্ডিং টু রুটিন, তার থেকে নেক্সট 24 আওয়ার্স এর মধ্যে স্ক্যান করে ছবি তুলে পিডিএফ করে সিঙ্গেল ফাইল ইমেল করতে হবে। ঠিক আছে? আর ইমেল করার সময় সাবজেক্টে কি লিখতে হবে সেটা আমি বলে দেবো হোয়াটসঅ্যাপ গ্রুপে, এবং দিস ইজ ম্যান্ডেটরি। আই উইল চেক দিস থিংস রেগুলারলি। ইফ you are not sending these emails, then I will take action or I will report the HOD or whatever may be. So this is one mandatory requirement. So I hope this is clear to everybody. Taito? Marilina, is it clear to you?
Yes, sir.
Okay. Okay. So today I shall start the first topic of this electronics. This is bipolar devices. Did you download this one?
Yes, sir.
Yes, sir.
Okay, okay. So I will discuss this topic, start discussing these topics. Okay. So can you see the screen in your device?
Yes, sir.
Okay. So the book I suggest you to follow for this topic is Integrated Electronics by Milliman and Helkias. It's given on the syllabus also. So for this topic, you can take help from these books, or you can go through any other electronics books. It's very easy, not so difficult. Okay. So before going to the main topic, let's have some recap. All of us, we know about the atomic structure. At least we have some basic idea about atomic structures. Okay. So first theory regarding atom, I mean accepted theory regarding atom was given by Thomson. It was electron band theory. যে কি যে then Rutherford's theory. Rutherford's theory was concrete theory, or first very much acceptable theory. So I am not going details in these theories. In next semester, I will teach you spectroscopy, where I will discuss this thing in details, this atomic theory and these things. So the Rutherford theory, I think you know these things a little bit. There will be a nucleus in the middle of the atom, and all positive charge accumulates within this. Then electrons revolve in circular orbits surrounding this, and most of the atomic part is empty. He concluded this by interacting, alpha particles in an metallic foil, and observing the corresponding output, he did all this conclusion. Okay. And he told the balance between electrons and this electronic charge, that is repulsion between electrons and attraction between electrons and protons, that is nucleus, is balanced due to circular motion through this centrifugal force. So we will discuss it later. Here is not my topic. Okay. Then the main issue was in this theory, electrons are charged particle, and charged particle when rotates, then it radiates energy. And if it's radiating energy, then there could be a possibility, according to Maxwell's theory, charged particle when rotates radiate energy. So if it's releasing energy, then there may some situation when attraction between nucleus and electrons will dominate over the repulsion, then electrons will come into the collide and come into the nucleus. So stability was, uncertain. To overcome this, Bohr, what he did, he take the use of this, some information from this Rutherford theory, and he applied it with the Planck's quantum theory. So Bohr's theory was a mixture of classical and quantum theory. Rutherford theory was totally classical based. And he suggested that electrons can move only on some specific orbits, not in all anywhere orbits. This is one point. And another point he suggested that normally they are not radiating energy, only radiate or absorb energy when there is some jump by the electrons from one orbit to another. And another is the angular momentum. MVR is integral multiple of h by twice pi. Integral multiple of h by twice pi. That is quantized. So he used both quantum theory and then classical theory, combined this and given idea like this. Okay. So all positive charged within the nucleus. Then there will be some orbits where electrons may lie. Okay. And normally they are not jumping from here to here or here to here, not jumping. Let me make it a little bit slower. Okay. And when jumping from here to here, that is lower level to higher level, then it absorbs some energy. That is, you have to supply some energy to the electrons. And when it comes from here to here, then it will release some energy. And he gives an idea, this energy key, the difference between these two energy is equal to h nu. Okay, nu is the frequency of radiations. Okay, so this was mainly Bohr's theory. He also named there is this orbits 1, 2 like this, and 1 corresponds to K, L, M, N like this. Okay, and there is also a small theory. Number of maximum electrons can be occupied in a particular orbit is 2n square, where n is equal to this KL 1, 2, 3, etc. So in this way, if you have an atom with say 6 electrons, then say this is your nucleus, then in the first orbit 2n square means 2 into 1 square means 2. Say 1 electron, then another electrons. But in your take an example, you have 6 electrons, so next maximum can have 2n square means 2 into 2 square means 8. So we have taken example of atom having 6, so remaining 4 will lie here. Okay, and there may be other orbits, but these are empty. Okay, and Bohr's theory also gives idea about the distance from nucleus to these orbits. So this is R2, this is R1 like this. So there is a formula. I am not going to the deduction of this formula. Okay, just telling you, you can check or do. It's there in the school also, but in atomic spectroscopy we will discuss it in detail. So the radius of nth orbit is 5.3 into 10 to the power minus 11 n square by z, where z is corresponds to the atomic number of the atom of which we are interested, and n is the number of orbits. So from here, putting the value of n and z, you can have idea about the radius of different orbits in a particular atom. Okay, so this is one issue. And also, according to Bohr's theory, energy of all the electrons in a particular orbit, for example, in our example, in first orbit, there are 2 electrons, so both these 2 electrons have same energy. Similarly, in second, there exist 4, so these 4 electrons will have same energy. But in spectroscopy, you will see it's different. Normally, if electrons having same energy, we say it's degenerate. So I'm not going this. This is a topic of spectroscopy. Okay. So here, Bohr has given, using Bohr's theory, we get an expression, okay, to have idea about the energy. So En is the energy of the electron in nth orbit. All the electrons in nth orbit is equal to minus 13.6 into z square minus n square. Again, z is the number of atomic number of the atom we are interested. N is the orbits where the electrons is lying. Okay, so you can have an idea. So this is by Bohr's theory. Okay, so if you take the example of, say, hydrogen atom, so and if you use this formula for hydrogen atom, we know Z is equal to 1. Okay. Okay, can you hear me?
Yes, sir.
Okay, so I give responsibility of any of you. If there is any problem, then you can give me call immediately. Okay, only one, not everybody don't call. Okay, so you discuss among yourself and take the responsibility by any of you. So tell me the name, who will call me? I am waiting. So no one will call me. I'm not sure. So who will call me? Vidyut?
Yes, sir.
So you attend class regularly or not?
Yes, sir. Regularly,
Okay.
sir.
Okay, so you note down my phone number. My phone number is there in the WhatsApp group. Okay. So if during my discussions, if somewhere you don't listen and you feel ki my internet or any problem, then you can call me. Okay.
Okay,
This
sir.
is I assign you for this task. Anyway, so if we take the example of hydrogen atom where Z is equal to 1, so by putting Z is equal to 1, we can calculate the energy of electrons lying in different levels. For example, for n is equal to 1, this is minus 13.6 electron volt. So we can say that there is a simple line, okay, corresponds to, say, these are n values. We say that this lines corresponds to minus 13.6 electron volt in case of hydrogen atom, and all the electrons lying in this level will have this amount of energy. Similarly, for n is equal to 2, by putting 2, we can have this value. Okay. So we can say that all electrons in hydrogen atom lying in n is equal to 2 will have this amount of energy. Similarly, for n is equal to 3, in this way, for n is equal to infinity, n is equal to infinity, this is 0, because divided by n square. So infinity, so it's 0. So maximum energy, this is 0 for all atom. The energy corresponds to infinity level of any atom is always 0, because divided by infinity is always 0. So we can say that maximum energy of an electron within any atom, not only in hydrogen, always should be negative. If it is 0, that means electrons gone in infinity. Okay. And if you want to take out any electrons from the atomic system, then you have to make the energy of the electron 0. That is, you have to supply the energy up to what? Say, in hydrogen atom, 1 electron, 1 H1 here. So it has minus 13.6 electron volt energy here. So 0 minus 13.6 electron volt. That is, you have to give 13.6 electron volt energy. For what? To make the energy of this electron 0. That means to move these electrons to infinity. So we say this then this atom is ionized, because normally atom is bound system. Bound system for what? With respect to electron, because within the atomic system, energy of all the electron is always negative, and it cannot go out of the atomic systems. It's bound system. Only if energy becomes 0, then it will go out, and in that case we say it ionized. In case of hydrogen atom, an ionization potential is like this. Now, if you give energy to these electrons, according to Bohr's theory, if the energy is equal to this amount, that means difference between E1 and E2, that is minus 3.39 minus 3.6. Okay, that means it's 10.2 electron volt. If you provide this electron, it will go here. If you give energy difference between these two, here and here, it will go here. And this is equal to minus 1.51 minus 13.6. Again, this is excited. We say this is excited. And if it's go here, we say it's ionized. And this is ionized potential. And this, if electrons go from its original level to other levels, higher level, we say it's excited, atom is excited. And in this case, you have to supply energy, and this energy is known as excitation potential. And it's different for different levels, different pair of levels. If you want to excite one electron from here to here, you have to supply minus 1.51 minus 3.39. And it's difference of সমান দিতে হবে। এগুলো হচ্ছে excitation potential. Okay? So we can draw a diagram like this. It's a set of horizontal lines. Each line corresponds to a certain value of what? Energy. Of whom? Of some electrons. Corresponds to a particular atom. এরকম অনেকগুলো লাইন টেনে দিতে পারি, আমরা দিয়ে করতে পারি। এই ধরনের ডায়াগ্রামকে বলে এনার্জি লেভেল ডায়াগ্রাম। Okay, so energy level diagram gives you idea for any particular atom, number of electrons of that atom having the values of energy. How many electrons in an atom have what amount of energy? All the atoms, for example, lithium. If you take lithium has 3 electrons, 3 Li. So in Na is equal to 1, it has 2 electrons. Here, N is equal to 2, 1 electrons, although it can possess 8, but since it has only 3 electrons, so it's like that. And energy of this one, say E1, you can calculate easily by putting Z is equal to 3 and N is equal to 1 in this expression. Similarly here also. This is empty. Like highest corresponding to infinity is 0. Okay, so this is energy level diagram of lithium. So you can do it. Okay. Now, for any specific atom, the lowest energy level, that is corresponding to N1 is equal to 1, is known as ground level. And these are the higher level. This is energy level. This is then that. For example, for hydrogen atom, highest energy level occupied by electron is N is equal to 1, because only one, it's lying on the N is equal to 1. For lithium, highest here. Okay. So for lithium, this is known as valence level. This is known as valence level. Okay. And this is known as conduction level. Valence level for any atom is the highest energy level where electron exists. This is known as valence. And just next level after the valence level is known as conduction level. So in case of lithium, level corresponds to N is equal to 2 is valence level. Level corresponds to N is equal to 3 is the conduction level. Similarly, if you take the example of say sodium. Sodium is equal to 11 Na, 11. Z is equal to 11. So for N is equal to 1 level, that is E1, 2 electron. E2, N is equal to 2. 2n square means 8. So 5, 6, 7, 8. আরো একটা রয়ে গেছে E is equal to 3 তে 1. You can calculate these values by putting Z is equal to 11 and N is equal to 1 to 3, etc. So you can have idea about the energies of these electrons. Okay. So then this is N is equal to 4, E4, 5, like this. Then একটা level গিয়ে N is equal to infinity. This is 0. So this is for sodium. So for sodium, this is your ground level, and this is your valence level, N is equal to 3, and this is your conduction level. Okay. So in this way, you can have an idea about the energy levels. But while you are talking about electronic device, normally we always talk about band, rather level, conduction band, valence band, like this, forbidden energy band, like this. Okay. And this is related with semiconductor. And normally electronic device, and most of the devices are based on semiconductor. So here we will study the property of semiconductor. Okay, then we will go to the devices. Okay, so why bands in case of solids? This is because, say, we have taken an example of lithium. Lithium has 3 electrons in a single lithium atom. This is for a single energy level of a single lithium. You see ground level 2 electrons, then 1 electrons. Okay, then N is equal to 3. No, so we say this is conduction level, this is valence level for lithium atom, not lithium solid. Now let us take a piece of lithium consisting of 100 lithium atoms, because if you are talking about solid, it's an array of atom or molecule in an organized periodic order. Okay, so let us consider, just for understanding, a piece of solid of lithium consisting of 100 atoms. In that case, we can think of a system where 100 energy levels, and for each n is equal to 1 having 2 electrons. So there may be a system like this. In principle, ideally, all the electrons of lying in n is equal to 1 should have same energy value. For example, for first atom, these 2 electrons will have same energy. Then second atom, theoretically it should be same. Okay, but depending on the construction of the atom, okay, or as well as environment, okay, condition, there may be a slight variation, but it's very minute. So we can think of a condition, okay, system of what? P 100 energy levels corresponds to n is equal to 1 of 100 lithium atoms, where 200 number of electrons will lie. But since electrons are identical particles, again it's a topic of spectroscopy or atomic theory, we will discuss it later. Electrons are identical. Identical particle means, Mr. A, say you have 2 persons, A and B. A and V. This is the name. So you can explicitly tell who is A, who is B. Why? Because there are some visual difference in the persons or physical world objects. At least there could have some microscopic differences. By observing which you can say that, okay, this is A, this is B. But in case of electrons, you cannot see any difference physically. Okay, so it's difficult to distinguish this 200 electrons, Jeki, having some minute variations in energy. Minute means very less variations, say of the order of micro to nano order. Okay. In case of electrons, you cannot say that, yes, this is A electron, this is B electron, this is C electrons, because you cannot observe physical difference. You cannot put tag also there, because these are subatomic level size. So they are identical particles. Then how you distinguish the levels? There are some theories. So we are not going there, but these are identical particles. Okay. You can design wave functions and other things also. Energy eigenvalue. With this, you can differentiate. But this is another theory. We are not talking here. So here we can think a system of solid consisting of 100 lithium atom will have a band of energy. Band of energy means corresponds to 100 energy levels for 100 n is equal to 1 of 100 atoms. And each n is equal to 1 is closely spaced. Why closely? Normally, theoretically, this should have same value, but closely because depending on the interaction of the atom with the medium. Okay. For example, if an atom is lying at the boundary of the solid, it will gain some energy from the outside. If it is some interior, then extent of gain is different. Okay. So the energy of the electrons will be little bit variations. But since these are identical particles, we cannot say which electron is where. So we can think of a system that corresponds to 100 energy level of 100 ground level of 100 atoms, a level rather than, a band rather than a level. Band for what? The minute variation of energy in of electrons in these levels. Of what? The different atoms. 1 নম্বর অ্যাটমের এনার্জি এরকম, 2 নম্বর অ্যাটমের এনার্জি এরকম, মাইনিউট ভেরিয়েশন। কিন্তু 1 নম্বরের যে দুইটা ইলেকট্রনস আর 2 নম্বরের দুইটা ইলেকট্রনস, এটার মধ্যে ডিফারেন্সিয়েট করা ডিফিকাল্ট। কাজে ইউ ক্যান থিঙ্ক অফ এ সিস্টেম যে এরকম একটা ক্লোজলি স্পেস ব্যান্ড অফ এনার্জি, হোয়ার 200 electrons of 100 atoms occupy. That is 100 energy states are overlapped, okay, and they form a band. Similarly, 100 this level will form another band where 100 electrons will lie. 100 here, 100, because this level consists 1 electrons. Okay. Similarly, this is corresponds to n is equal to 3. That is 100 conduction level is overlapped. So this will form again a band. Okay. So in case of solid, always we will think of a band where, for example, lithium here, 200 electron can lie here. Okay. Say within this band, maybe this is corresponds to n is equal to 1 of the first atom. Maybe this is n is equal to 1 for second atom. N is equal to 1 for third atom, like this, 100, like this. Everywhere 2 electrons, but we cannot say that which are these 2 electrons, because these are identical particles. We cannot give name, we cannot give tag to them. So we can say that they can move anywhere in this band, this 200. Similarly, 100 here can move. Okay. And according to Bohr's theory, if we push them from here to here, then again for 100 atoms, there will be 100 electrons and it can move here. So this is conduction band. So in this way, in case of solid, we say that bands instead of levels. Okay. And the mainly electronic property of the atom, whether it's single atom or in solid, it mainly characterized by these valence electrons. When you supply energy, obviously they will gain some energy, and depending on the amount of energy, they may jump from one level to another. So normally in electronic device, energy supplied or taken out is related with this valence band and conduction band. Okay. And once electron is jumped from valence band to conduction band, then we say that this is available for conduction. Okay. So in this way, we will see. Okay. And this gap, again, you see, this gap between valence level and conduction level is known as forbidden energy level. Forbidden energy level means no electron can lie here. If you put energy, say this is your EJ. If you put energy equal to EG by 2, say EG by 2 to this atom, it does not mean that this electron will lie here, because no level is there. It's quantum. So it will not go. It will again come back here. So in this way, if you go on increasing, once it gain energy Eg, it will go here. It is available for conductions. So this region is known as forbidden, because no electron can occupy here. Okay. So for 100 atoms, again an overlap of 100 these gaps. So we say that forbidden energy gap. This is written as Eg. Okay. So if this gap is higher, that means this system have high resistance, lower conduction or conductivity. Okay. So based on this gap, solids are characterized as conductor, semiconductor, insulator, etc. These are the resistivity. Okay. Or in terms of conductivity also, you can say that. Okay. For example, say germanium is a semiconductor, silicon is a semiconductor. These two are very famous, and now most of the electronics are based on silicon. But people are now interested in other semiconductor also. Inorganic semiconductor like gallium arsenide, cadmium sulfate, indium phosphate. So many systems are there. Okay. are coming up. But normally, most of the electronics are based on silicon. Okay. So in case of silicon, this gap is of the order of 1.1 electron volts. In case of germanium, this is 0.72 electron volt. Okay. And based on this gap, they characterize this conductor, semiconductor, insulator. So if it's semiconductor, that means depending on the material, you have to, the resistance is of this order. So accordingly, you have to supply particular amount of energy to push the electrons from the valence band to conduction band. Conductor, same, but of course the energy requirement is very less. Normally, even in ambient conditions, always there exists some electrons in the conduction band. That's why it's conductor. But semiconductors, normally electrons are almost empty conduction bands. When you supply energy, then it will go jump. Insulator, gap is very high resistance, but you can use it as a conductor. For example, a rubber, a wood, you can make it a conductor, but in that case, you have to supply very large amount of energy. You can use for conductivity, for conduction of electricity. But in that case, energy requirement is very high. Okay. So anyway, so normally semiconductors are characterized, or conductor or whatever may be, semiconductor is a solid where gap difference between the conduction and valence band is of the order of like this. Then we say that this is semiconductor. And nowadays in electronics, it's semiconductor based. Okay. And in case of semiconductor, mainly people are using silicon. But now people are working for other also. Okay. So now you know that, and again, silicon number of atoms in valence level, they have 4, germanium also 4. You know this kind of things. Okay. So we are not going there in details. Okay. So in semiconductor physics, there are 2 types of semiconductors. One is intrinsic semiconductor, another is extrinsic. Intrinsic means pure, or extrinsic means impure. Pure semiconductor, 2 types. One is silicon type, one is germanium type. And most of the electronics, almost say 90% or more, is silicon based. In case of impure, again, it's N type and P type, and based on the doping. Okay. Another thing, we will see it later when we will see the energy level discussions. Normally in conductor, the conduction is based on the electrons available in conduction band. But in case of semiconductor, the conduction, because normally conductor electrons is already there in ambient condition in the conduction band. So by applying proper biasing, you can make this electron move. So you will have conductivity. But in case of semiconductor, what you have to do, you have to push electrons from this valence band to conduction band. So in conduction band, you will have a free electrons, and in valence band, you will have a shortage. So this shortage is known as hole. So for example, say if say in your semiconductor here you have 100 electrons, corresponds to say 100 atoms. Say this is just an hypothetical example. So if you supply energy and say 10 electrons move here, then you are having 10 free electrons. Okay, and 10 hole here means shortage, because covalent bond will break and electrons will jump. Okay, but since electrons are identical particle, you don't know which bonds are breaking, which electrons moved. Okay, so when you apply bias, there is a tendency that other electrons which are not broken can jump from their place to this empty space. That means electrons in the valence band can also move, but it depends on the hole. So we say it's hole current or movement of hole. Actually, this is not movement of hole. Electron current is due to the movement of electrons in conduction band, or hole current is due to the movement of electrons in valence band. Both current is due to movement of electrons. One is movement of electrons in conduction band, another is movement of electrons in valence band. Okay, and when you apply field, you will see conduction band is empty, only free electrons exist. So if you apply same amount of potential from outside, you will see the tendency of the movement of electrons in conduction band is more, because here electron will move based on the hole, but this level is highly occupied. Okay, so there is some traffic jam. So in this way, we say that mobility of electron is higher, because here electron will move from one hole to another hole, and hypothetically we say that hole is moving, but this probability is lower for same applied field compared to the movement of electron in conduction band. So in this way, we say that mobility of electron is higher than mobility of hole. Mobility means drift velocity acquired per unit field. Okay, মানে সেম ধাক্কা দিলে কার কতটুকু মুভমেন্ট হবে, ড্রিফট মানে জোর করে সরানো। ওকে ওকে, so in case of there are other semiconductor other than impure, where we do some doping. Doping means, for example, these are germanium and silicon. When we give energy from valence band, electron moves to conduction band. Accordingly, you will have hole or you will have electrons for movement in conduction band and valence band. This is for pure case, but in impure case, we will accelerate the probability of movement of electron or movement of electron to the conduction band, or taking out of electron from the valence band. By how? By putting other atoms within the system. For example, if we put atoms where some extra electrons exist beyond covalent band, that is, say, pentavalent, then what will happen? Out of this 5 valence electrons, this we say donor, 4 electrons will covalently bonded with germanium or silicon, and then 1 remain free. So even if you give minute amount of energy, it will move to here. So probability of movement of electron from valence band to conduction band in case of pure is less. In case of impure is higher, because you are giving additional electrons from outside. Similarly, in case of p-type means hole. So what we did we add some other or foreign atoms which have one valence electron less than the silicon. For example, say 3 wala. So in that case, 3 will form bond with silicon and 1 remain empty. So when you just give some minute energy, then covalent bond within the silicon will break, and it will go form covalent bond to this empty electron or free electrons within the donor atom. So probability is higher. Okay. So conductivity is affecting. So anyway, so we have 2 types of mainly semiconductor. One is intrinsic, one is extrinsic semiconductor. In case of intrinsic, we have silicon, germanium. Extrinsic, again, depending on the added atom. If it is electron rich, we say it's n-type. If it is electron short, then we say it p-type. Again, n-type you can have using silicon, using germanium. Here again, silicon, germanium. Okay. So this is basically, now there are even single molecule can act as an semiconductor. I will discuss it at the end of this topic later. Okay, give some example, but these are some very basic things. Now, band structure of pure semiconductor. Band structure means we will mainly talk about valence band and conduction band and the phenomena within these 2 regions. There will have other energy bands or levels. So we are not interested, because the conductivity or optical behavior mainly governed by the electrons lying here or moved here. Okay, so we are concerned about this. So in intrinsic semiconductor, since it's a solid, so we will have a valence band here and a conduction band here. This is the energy gap, and number of electrons or holes, whatever may be, it depends on the number of atoms. Okay. So say at absolute zero, so all electrons are in the valence band. If you give some energy, and of course energy should be equal to this Eg. Okay, so this Eg will help to break the covalent bond within of the electrons from valence band, and it will push here. Okay, so one electron if jumps from here to here, then one hole will create. Hole means shortage of electrons, not finding the electrons, absence of electrons. So we say that this is hole, this is electron. So we can create as many as hole or have electrons here by manipulating the amount of energy we are supplying. So if you see or discuss the energy level, energy band, in case of pure, mainly we will have a conduction band like this and a valence band like this. This is energy gap. Okay. And mainly current in case of such semiconductor is due to drift of electrons in conduction band and drift of holes in valence band. So current means charge particle should be moved. So drift means you have to push some push from outside. Here push in the forms of potential, or you can supply using some battery. You can like this. So if you give some potential from outside, this hole will move. Hole move means actually electrons will move here from here to here. So hole will be here. Then from here again will jump here. Then hole will here. So actually we say that this whole current or movement of hole is opposite to the movement of electrons. Hole is moving this direction. Okay, and electron will move here. So current in this type of semiconductor is mainly due to drift of electrons in conduction band and drift of holes in valence band. Now, in case of impure semiconductor, again, like pure one, you have conduction band, you have valence band. Okay. Now, in case of n-type semiconductor, your electron is rich in this material for conductions. That means normally pure, you are giving energy so that one electron from here jump to here. But here, what we do, we add some extra foreign atoms which can easily give electrons from this atom to here. That means energy required to transfer electrons from this donor level to this conduction level is lower than the pure one. So we can say that these donor atoms will lie close to this conduction band. So for this, to represent this, what we can do, we can identify a energy level corresponding to donor atom. We say donor level where donor atom will lie, and you see the gap is lower than this gap, and easily electrons can jump here. So here, mainly most of the conduction is due to electrons available here. So in n-type semiconductor, conductivity is mainly due to drift of electrons available here. But of course, there will be some electrons here from here also. And this is due to rupture of covalent bond. But probability is very less because small energy, electron will jump from here to here. Probability to jump from here is less. But if at least few amount of electron jump from here, how? By breaking of covalent bond, then it will leave a hole here. So we say that this is minority carrier. Okay. So in type of n-type semiconductor will have an energy level close to conduction band, corresponds to the donor level, and main electrons available here is due to the donor level, donor atom, and each donor atom will give an electron here, and few electrons contributed from here to here. This is minority due to breaking of covalent bond, and here also same number of hole will be there. So number of electron will be maximum. Okay. In case of conduction band, in case of p-type semiconductor, we said that p-type where hole rich material. Hole rich means positive charge means, and where hole is created in valence band. How? By leaving one electron by breaking of covalent band. So normally in pure, electron jump from here to here by breaking covalent bond based on the energy supplied. But in case of p-type material, what we do, we add some other foreign material which have shortage of electrons and easily can take one electron from the valence band of the original semiconductor. Okay, so in that case, we say that there will be a level where acceptor atom will lie, and this acceptor atom each acceptor atom can accept one electron from here through breaking of covalent bond, leaving one hole here. So number of hole is equal to the number of acceptor atom, ideally. However, still based on energy, very less number of covalent bond can break and push the electron here also. So we say that this is minority carrier. So mainly the current is due to drift of the holes in this valence band. Okay, means drift of electrons here. Very less number of electron is here. Okay, so this is your p-type semiconductor. And in case of n-type material, number of electron is very greater than number of hole. In case of p-type material, number of hole is very greater than number of electrons. Okay. So till now, if you have any question, you can ask me. Kishalay Devnath.
Yes, sir.
Till now is okay?
Yes, sir. Yes, sir.
Okay. Okay. So we have seen that in case of semiconductor, if it is pure, then the conduction is mainly due to the electrons available in the conduction band and holes available in the valence band. Okay. So now we want to have idea about the concentration of the electrons or holes in conduction band or valence band respectively. Okay. So we will try to have idea about the carrier concentration in an intrinsic semiconductor. So in an intrinsic semiconductor, each electrons, okay, available in conduction band for conduction leaves behind a hole in the valence band. So number of electrons in the conduction band is equal to the number of holes in valence band. So let us see the electrons concentration in conduction band. Okay. According, so let us say this is a picture say of conduction band. Say we designate say EC is the lower level of the energy of the conduction band. E is an arbitrary level, and E plus DE very closely spaced level corresponding to E. Then, according to free electron theory, the number of the number of energy states per unit volume of the material in the energy range between E and E plus DE is given by NEDE is equal to 8, this kind of expression. This is number of energy states within this range. Okay. Now, for simplicity, we replace this constant using gamma. Okay. Then, according to, you see, these electrons are fermions. So, normally, a Fermi-Dirac probability distribution function is applicable here. And Fermi-Dirac distribution probability say that probability of finding electrons in a specific energy range is given by Fe is equal to 1 divided by this one, 1 plus E to the power E minus EF by kT, where EF is another interesting energy. Okay. So আমরা দেখছি যে কি in case of semiconductor, electron, say if it is pure semiconductor like this, if you supply energy from outside, atom will absorb energy, and if, say, this is your Eg, oh, it's written here, this is your Eg, if you are giving energy, say, less than Eg, so it will jump, then come back. Okay, then slightly go on increasing, then again jump, come back, again jump, come back, again jump, come back. Okay, but never it will go here. It will go only when the supplied energy is Eg. Okay, so EF, this is known as Fermi energy. This is an hypothetical energy value or level, corresponds to the energy of the electrons at absolute zero. আমরা বলেছি কি absolute zero তে এখানে কোনো ইলেকট্রন থাকবে না, all electrons are here. However, based on the energy of electrons, there could be a probability যে এরকম জাম দিয়ে যখন আমার এসছে যে পাওয়া যেতে পারতো, এরকম করে 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 আয়া পড়ছে, তাহলে ম্যাক্সিমাম হায়ার এনার্জি লেভেল, hypothetical, কাল্পনিক, where electrons could have been found, কিন্তু আসলে নাই, বুঝতে পারছো? বাট this is corresponds to this Fermi level. This is a probability of finding electrons. This is a hypothetical energy level corresponding to absolute zero temperature, okay, where electron could have been found, but no, physically invincible, there exist no electrons. So this is Fermi level. Okay, so now when you will supply energy to move from valence band to conduction band, already your electron is having energy of the order of EF, because it's jumping from valence band to EF, again coming, jumping. So when you will give extra energy, it will add up with EF and adding. When as soon as it become EC, then it will go to conduction band. Okay, so depending on the supplied energy, we say that ki probability এটা কোথায় যাইবো, conduction band কোথায় যাইবো, actually এটা EC minus EF হলে এখানে চলে যাবে, EC minus EF হলে এখানে যাবে। আমরা যেহেতু E ধরেছি যে এখানে পাওয়ার probability সেটা হচ্ছে E minus EF, এইজন্য according to Fermi-Dirac distribution function, this is the probability of finding electrons in this region. Okay, where EC is the lowest level of conduction band, EF is the Fermi energy level. Now, this is corresponding to EF, so E level, finding of electron in E level. Now, within E and D, if number of electrons finding is number of energy state NED into this Fe, because Fe is probability of finding in E, or within E and D there is a energy range NED. So NED into Fe is the number of electrons you may find within the range E plus DE. Okay. Now, if you want to have idea about the total number of electrons within this range, you have to sum up all the energy range. That means you have to integrate from EC to E top. In that case, we can write an expression NC, where NC is the number of electrons lying in the conduction band, is EC. এখানে কেটে গেছে EC to E top, NED FE integrate. E top corresponds to upper limit of the conduction band. ওকে, আচ্ছা এরপরে এটা পিডিএফ করতে গিয়ে গন্ডগোল হয়ে গেছে। এটার পরে যাবে, তুমি মুভ করো, এটা যাবে, এটা হোল্ডারটা এসে গেছে এই যে এখানে, বুঝতে পারছো ব্যাপারটা? পেজটা উল্টা লেগে গেছে। এই যে এনসি, এটার পরে এতটুকু অব্দি বুঝতে পেরেছো? এই মাঝে মাঝে রেসপন্স না হলে বোঝা যায় না তোমরা আসো না নাই চলে গেছো, একা বলে যাচ্ছে।
Yes, sir.
বুঝতে পেরেছো তো? হ্যাঁ, তাহলে এনসি হচ্ছে নাম্বার অফ ইলেকট্রনস উইদিন দি হোল কন্ডাকশন ব্যান্ড। কিভাবে পেয়েছি আমরা? এই এনার্জি রেঞ্জকে ইন্ডিকেট করে পেয়েছি। এরপরে এটা চলে গেছে, এটা ভুলের জোড়া লেগেছে এইভাবে এই জায়গাতে। সো উই হ্যাভ দ্য এক্সপ্রেশন লাইক দিস, এই যে ইন্টিগ্রেশন ইসি টু ই টপ NED FE. Now we will apply some assumptions. If you look into the diagram, you will see EC very, very greater than EF, because if EC could have very close to EF, then physically you could have found electrons in conduction band. কিন্তু বেশি বলেই যেতে পারে না। আবার E minus EF very, very greater than KT, because KT is very, value of KT is very less. Or E is higher than EC. So E minus EF very, very greater than KT. In this case, E to the power E minus EF by KT very, very greater than 1. Okay, very, very greater than 1. So in the probability distribution functions, you can compare to the other part, you can neglect the 1. Okay, why? Because this part is very, very greater than 1. Okay, so in the denominator, you can see the expression of this one here. E to the power EF minus KT very, very greater than 1. So you can neglect this one with respect to this part. So in this case, Fe is equal to E to the power minus E minus EF by KT. এটা এখানে লেখা আছে। এই যে, this is one approximation. Another approximation is regarding the upper limit of the conduction band or upper limit of the integration. You see, from this expression, you can see that if you increase E, value of Fe decreases because it will increase the contribute more negative to the power of E. So value is more minus. Okay, so value of Fe, and the probability of finding electrons, decreases with increase in E. And this is very feasible also, because maximum electrons will take energy exactly equal to Eg, because Eg সমান পেয়ে গেলেই কত জাম্প করে চলে যাবে এখানে, কত এক্সট্রা এনার্জি নেবে না, নেওয়ার জন্য ওয়েট করে থাকবে না। বুঝতে পারছো ব্যাপারটা? কাজেই they will jump to Ec. So there is very less probability that electrons can exist in higher sides of the conduction band. So maximum electrons in the conduction lie close to Ec. So in that case, for the sake of calculations, we can write E top equal to infinity. So we applied two approximations. One corresponds to probability of finding of electrons, and then probability of finding of electrons with respect to the location in the conduction band. So by using these two approximations, we can rewrite. Now I request you to calculate this part. Okay, to calculate this part, we can rewrite this expression, number of electrons in the conduction band equal to E is equal to Ec2, E is equal to E top equal to infinity. Now we put the value of NEDE and Fe. Okay, so this is the expression. So this is we rearrange, just we took the common, because EC, EF, these values are constant, E are arbitrary. So we take common e to the power ec minus ef. যদি এটা তুমি ভিতরে ঢুকে দাও এটাই পাবে। বুঝতে পারছো ব্যাপারটা? So just rearrange for the sake of calculations, and then we apply integration through substitutions. E minus ec by kt is equal to x. In that case, we can write like this. এগুলো simple calculation দেখে নাও একটু এটা। From here, d is equal to kt dx. So when e is equal to ec, x is equal to 0. এখানে বসিয়ে দিলে e is equal to ec, x is equal to 0. E is equal to infinity, x is equal to infinity. So we rewrite the expression like this. Nc is equal to gamma e to the power this, then like this. Okay. Now we replaced this e using x. Okay. So again we reformatted the expression and we get an expression like this. And here we use an expression given in gamma function. You see, gamma n is equal to integration 0 to infinity x to the power n minus 1 e to the power minus x dx. This is equal to gamma n. So from here we write this one, root over 3 by 2. Sorry, root over means gamma 3 by 2. Okay. And gamma 3 by 2 is equal to half root pi. So we can have an expression like this. Nc is equal to nc e to the power ec minus ef by kt, where nc is equal to this. Okay. So this is the expression of number of electrons you can have in the conduction band. Okay. So you have to have clear idea about this expression, because in later part I will use this expression in few cases. Okay. So right now, if you have any questions, you can ask me. So what I told, you have to do calculation of these calculations, and after the class with homework, you have to take the photograph. You don't need to copy all the notes, only calculations, and then take the photograph, make a single PDF, send me by email. I will share you the email. Okay. So since no response, so I assume you all have understood this. So now we'll see the whole concentration in valence band. Whole concentration in valence band. So again, say we considered normally whole lies within the valence band. So EV, let us consider EV is the upper limit of the upper level corresponding to the valence band, EV. Okay. So EF, normally EF is not there, but based on the energy, available energy or ambient conditions, some electron will jump like this. So highest jump corresponds to EF. Okay. So EV energy corresponds to the top of the valence level. So again, according to density of state, if you consider two energy levels, E and E plus DE within the valence band, then you can write the number of energy states. Any DE is of the order of like this. Okay. Now a hole is nothing but an energy level. Okay. And simply this is the probability of not finding an electrons, because finding of an electron hole in the valence band equal to the not finding of an electron in the valence band, because you will find an hole only when one covalent bond will break and electron will jump from valence band to conduction band. So not finding an electron actually equal to the finding of an hole. So the probability of finding hole in valence band can be written as, because total probability is 1 minus Fe. Fe is the finding of electrons. Okay. So not finding 1 minus Fe. So we put this based on Fermi distribution functions. Then we apply some approximations. if E minus EF, you see E is somewhere here, EF is here. So if you E minus EF means more negative, this is very, very less than KT, then e to the power E minus EF by KT very, very less than 1. Ulta hoega sir, agata respect. In that case, Fe is equal to like this. So number of holes per unit volume means this probability distribution function into this one, NADE. Okay, and then we integrate from E is equal to bottom to E is equal to top, that means EV. E is equal to bottom to EV. Okay, now we apply another integration, approximation, that the factor E minus EF minus E by KT decreases rapidly as one goes down below the top of the, because নিচের দিকে গেলে value of E কি হবে তোমার কমবে. So in that this way EF minus E will increase and minus বেশি হবে, তার মানে value of this factor will decrease very rapidly. Okay, of what? Finding of hole is very less to the lower. This is very physically also possible, because say your electron, one covalent bond is here and one covalent bond is here. Now if you supply energy, then probability of breaking this covalent bond and jumping electron from here to here is higher than breaking here and jumping, because this will take higher energy. So it will go always close to the EV physically. Mathematically also same. Okay, so we can say that as long if we go the lower part of the EV, then probability of finding of hole, that means probability of breaking of covalent band and jumping to the valence conduction band is very less. So for the sake of the calculation, or to make it easier, we can consider E bottom corresponds to minus infinity. So we can rewrite the concentration of hole in valence band minus infinity to EV, this, then it also like as a উপরে ওই আমার গন্ডগোল হয়েছে লাগানোতে, এই জায়গাতে এসে গেছে এটা. Then PC is equal to a expression. Then we use substitution integration, again EV minus E by KT is equal to X. We calculated DE, we calculated the limit, we put it here. Okay, then we apply this formula from gamma function, and then we have an expression like this. PC is equal to NV. This. Okay. So this is the expression for hole concentration in valence band. So you calculate this part and check, and you take the photograph of this calculation also, make PDF, merge with the earlier one, then send me by email. Okay. So I will stop here today. Okay. So if you have any questions, you can ask me. Subrata?
Yes, sir.
If you have any questions, now I am asking rule number 1 to 10. If you have any question, you can ask me. If you don't ask, then I will assume that everything is clear. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. No question. Then 10 to 20. No question. Then 20 to remaining. So I assume all of you have understood everything. Okay. So tomorrow I will ask, and you do the calculations, send me the classwork by email. Okay. So tomorrow I'll see you tomorrow at what time? Our class? তোমরা কথাই বলো না, আমি বুঝতে পারলাম না ব্যাপারটা।
10 a.m.
হ্যাঁ, তোমারও কয়টায়?
10 a.m.
Sir, 10 a.m. sir, 10 a.m.
Okay. So I will take class at 10:30. Okay, 10:30. Okay then. I am closing.